Hello fellow skeptics, I'm Luther Name, and this is the 19th video in a series of videos addressing the broad issue of, is something wrong with modern physics? If so, what? And can it be fixed? Now in the last video I introduced some discussion on Einstein's general relativistic equation. There are a number of aspects of the use of that equation that deserve some further comment. What I'm going to do in this video is show how to fix it. And that is that it currently uses Newton's inverse square law and his point mass laws. And when we generate our orbital equations, which is for large objects, we're using approximations, and so our results are approximations. And in fact, where those current Newtonian laws that we use break down is just where general relativity is intended to be used, which is when objects are in close proximity. When objects are far apart, the dynamics reduce to basic Newtonian physics, which is that there's no significant perturbation on the interaction of the objects, and their interactions become more point-length when they're further apart. But the interesting things occur when the objects are in fact in close proximity, and that's exactly when Newton's laws tend to go off the rail. So what I'm going to do is talk a little bit more in generalities on how to fix it. Now, the interesting thing about Einstein's general relativistic equation is that it reduces to, under the right circumstances, to what we have been using for a century or more, which is the Euler-Lagrange equation for calculating trajectories and orbits and what have you. And it reduces to that. When we use it for orbits, like for planets, it reduces not just to the general multidimensional equation that Einstein produced, it reduces to a two-dimensional equation. Objects orbit in planes, like planets in the ecliptic, and therefore you only have two variables. One is the radius, movement of the radius, and the angular motion. And interestingly enough, that's what the initial solutions to the general relativistic equation reduced to, was the Euler-Lagrange equation in two dimensions. We've used the fake metric Minkowski produced, called the Lorentz metric, which contains the fourth dimension as an imaginary dimension associated with time. We can get to the same point that the original solution, Schwarzschild's solution among others, for the general relativistic equation much more simply, by just starting with the Euler-Lagrange equation, because that's what it reduces to. So we go through all these really difficult mathematical manipulations to take the general equation, and we make these approximations and assumptions and variable changes and do the things that applied mathematicians do, and we reduce it to the Euler-Lagrange equation. So what I'm going to do is I'm going to describe in a little bit more detail how we can get away from this point mass and the inverse square relationship, how we need to get away from it, and how we can simply reproduce the results from using the general relativistic equation for the orbit of large massive objects, and reproduce effectively the same effects. I don't know that there are any measurements that we've made that can distinguish between predictions associated with Newtonian gravity and with general relativity. You take Newton's gravity and you make a sufficiently large mass, and you can reproduce all the things that are identified through general relativity. There's nothing unique. There's a factor of 2 difference that crops up in there. I don't know that our measurements are making an attempt to discriminate between that. We've simply said, no, we'll use Einstein's equation as is, and the results we get, well, those are the results we're going to be using. But if we can get to the same general point using Newton's equations, then it behooves us to do a validation. Which one's correct? we're not looking, and perhaps there's no way we can really tell. I've looked at that some, and I'm not sure that we have the capacity at this particular point to make a distinction between whether Newton's gravity with modifications that I'll talk about, or Einstein's equation, which ultimately reduces down to the Newtonian, or at least to the Euler-Lagrange equation in 2 dimensions with a perturbation on it associated with other factors that we'll discuss on this. So with that, let me get to the visual materials that we're going to be talking about and go through a description which contains some tutorial, little background review so that it makes sense going forward in what we're trying to accomplish. This basically plays to the overall theme that I've tried to build into these videos, which is develop a roadmap, not solve all the problems, but identify how to solve the problems and how to move forward. A roadmap. These slides are basically a review. I've touched on everything that I'm proposing to do here, which is to take the approximations that exist within Einstein's general theory, his equation, and also exists within Euler-Lagrange equation as we use it. Uses Newton's point mass laws for gravity and for center of mass, and these are approximations. What I've done is I've showed that by going back and not using approximations, that the exact solutions are different than the ones that we use. And what I'm doing is basically going to insert all those things we've talked about, the correct form for these equations, and suggest that they go inside Einstein and the Euler-Lagrange equation for orbits. Remember that the Einstein's equation has so far, in practical sense, reduced to the Euler-Lagrange equation in 2-dimensional space, basic orbits. So everything that was said and has been said about Einstein's general relativity theory has to hold for Euler-Lagrange equation, since one's a subset of the other. So Einstein's general gravity equation is just that, and it's correct as it stands. It's a generalization, and it's valid. And there are Wikipedia articles on general relativity, Kepler, orbit problem, calculus variations, other things that will give anyone who's inclined or has the capacity the ability to basically go through and understand the details of what's going on with the Euler-Lagrange equation. So, as I said, the general relativity equation is an approximation. An energy tensor is an approximation. Newton's point mass gravity law is an approximation. Orbital angular momentum used in the dynamics for orbits, those are approximations. The Einstein relativistic perturbation in the orbital equation is not a single term function as identified by Schwarzschild. We'll show that that is another simplification, in that the one correction that Schwarzschild identified, or the perturbation that Schwarzschild identified for the Euler-Lagrange equation, is just a single term function. It's incorrect. So this is just some general background. I'm not going to go through it. It's just a timeline. The issue is that while Einstein's equation is correct, it is used incorrectly. Garbage in, garbage out. It is also true of the Euler-Lagrange equation. To first order, this can be directly addressed without recourse to Minkowski's spacetime, which is now called the Lorentz metric. So the correction required to make both the Euler-Lagrange equation and Einstein's equations accurate. Since the descriptions in our textbooks and what we're taught is simplifications, in some instances simply a dumbing down of what the true physics are. And I arrived at the true physics by simply not using the approximations and assumptions that were built into what we're taught in our textbooks. What we've done is then make a first order correction by just basically making these single swap outs. And there's nothing more to it than that. Here's 3 books that I've used. I'm familiar with them. They're good books. The middle one, Principle of Relativity, has Einstein's general paper, equation on the general relativity, which turns out to be his 1916 paper was a primer on how to develop that model. The model had been developed some years earlier, and in fact had been used by people to develop some first order solutions to the Einstein equation using the Lorentz metric. But what happened is that as time went by and so few people really understood the whole process, he published a paper. This is how I did it. This is how you get that equation. And he really doesn't solve any problems in that equation, but solutions had been proffered up to that point. This is a good tensor analysis book. I'll draw heavily on this one. It's by Sokolnikov, and the Calculus of Variations, which is another good book. I'm familiar with them, so that's why I use them. On the other hand, what I've done is I put together the videos here, and prior to putting the videos together where I had carried out analysis, I'd filled dozens of notepads, and things were out of control. So what I did was I wrote some books, and these books were merely a way of me ordering my thoughts and putting things down in a cohesive fashion, made sense out of a somewhat arbitrary order that things appeared in the working notes that I had. And so I put together these documents that are available up on Amazon, and I will go through them again after I'm completed this series of videos and make some improvements and get rid of some of the typos that are still lingering. So what are we talking about here? This is just real quick. This is what Newton said about what is the mutual attraction, gravitational attraction between two uniform spheres. This is the law. It's not the point mass law. What it is a more general law as defined by these statements here. These are merely representations. Spheres, you have a line going between the center. Here I call it R. Elsewhere I call it delta. And then I have another term I call delta prime, which is part of the analysis, not to be confused. So this is what Newton was really intending to get to. This is the only problem he could solve, though, using his early equations. And what we've done is we've generalized it to say it doesn't make any difference what shape, orientation, mass distribution objects are. The force is only directed along the line connecting the centers of mass of the two objects. This is a gross simplification. But it is good enough for technology and most purposes. In the book by Sokolnikov, he basically has this representation, which again just resets it up. You have a common point where you have these, it generalizes this particular geometry, and it's put together like this. But what happened was, at the time he wrote the book, this was really wasn't pre-computer days, but it was certainly pre-PC days, and people didn't have access to the type of software they could use to solve the problem. So he simplified it the same way that Newton had. He let one of these objects become a point mass object. And so what we have is, this is what was actually solved. And this is basically just says that if you make one of the objects a point mass, this will always turn out to be just a point mass. You just summing over the volume mass, and what you get is a mass. And so we wind up with this very simple form here. Again, instead of using r squared, I put in delta squared. That's just a nomenclature change on the thing, but it means the same thing. Delta equals cap r in this case. And it'll always reduce to that. You get no sense of what the volume distribution is or anything else relative to the object. I use this type of geometry, and this is just to make it clear that you can't set up a general equation. I set up a cylindrical geometry, and I defined the spheres in cylindrical coordinates. You can define it in spherical coordinates, but this is a little more flexible because I can make the z-axis common. And when I put the two spheres together, and then when I go and make my integration around one sphere and around the other sphere, I have them linked together through a common value, ultimately reduces to delta, the distance between the center masses of the two objects. Now, the first thing I did was I solved for the orbital angular momentum. And in cylindrical geometry, this is what it turns out to be. Now,
if we use a center of mass, well, this is what we get. We get center of mass value. This is the one that's typically used and is used. Nobody uses this, even though we do calculate something like this. We're looking at moments of inertia. So we know how to do it. We just never have done it. And when you calculate the orbital angular momentum, which is required in the Euler-Lagrange equation for orbits, what you wind up with is the orbital angular momentum doesn't follow the normal. This is a calculation divided by the center of mass value, which is the one that we normally use. And this can see that it can vary dramatically. This is the distance between the centers of mass of the object, it says, as a function of the diameter of one of the objects. And then I made the other object, the distance separated as just a multiple of that. So I could draw a curve. Using numerical integration, what we find is that when you have close encounters, two uniform spheres, they would come within to this point. And you can see that the orbital angular momentum varies vastly from the center of mass value. That's the first correction you can make. Now, the second one, this is what the mutual force between them is. This is just another representation using that stylized form of representation. These are supposedly two spheres, and these are the way we do it. And this dotted line here represents a reduction to the way Newton had carried it out. He couldn't carry it out any other way. In fact, until the computer age, we couldn't really do this. It was too arduous. And this is what the equation looks like. It has no analytical solutions, though it looks like it may have an elliptical function. Basically, it's impossible. You could try and develop series solutions, but they didn't necessarily converge correctly, and they led me to go into using Mathematica, because they can carry out these kinds of calculations numerically and graph them. And what we have then when we do that, this is just that same geometry now that was modeled mathematically. And when we graph it, this is what we get. We see that I used Mercury. I used the relative size of a uniform Mercury orbiting a uniform sun. And this is the distance as functions of solar radii of the orbit of Mercury, and it's elliptical, and you can see that it varies from about 68 to 66 here to 100 solar radii. This is the distance of the elliptical orbit. And if you look at the mutual forces calculated using Newton's general law, what you wind up with is variations that are up, above, and below. And so what you wind up with is, since any deviation from an inverse square law will cause the orbit to perturbate slightly, what happens is over part of the orbit it advances, and over the other part of the orbit it is retarded. And so what happens is, after a full cycle, you've got some net value, and that's so small that it takes 100 years worth of observations to get any deviations that you can measure and hang your hat on. So the order of magnitude is nominally correct, but it would have to be carried out. Again, these are uniform spheres. They don't have the mass distribution, and because the numbers are so small, it's very difficult to make these observations. It's doubtful that we know how to make the observations that would observe this variation in the mutual force, or via the perturbation or the advance and retarding of the perihelion of the orbit of Mercury. I'm not sure that we can measure that.
So at this particular point, I believe I've made the case for, is there something wrong with physics, modern physics? And the answer is yes. There's something wrong with still other physics that isn't necessarily modern. What is it? I've identified any number of these anomalies, including probably the most egregious, which is a failure to use our knowledge of physics for inertial and non-inertial propagation, and coming up with absolutely fallacious descriptions of what we think special relativity was all about. And then going on into general relativity, you have the issue of the Lorentz metric, which is the Minkowski 4-vector. Whether or not you believe Lorentz metric itself is flawed, I personally think that it may be, but what I've identified are other ways in which general relativity, the general relativistic equation Einstein developed, is wrong. Relates to point mass, point forces, point everything. Whereas, as pointed out, once you go back to Newton, you can identify the fact that we've simplified things because we couldn't do more complicated things, couldn't do the exact physics. But now that we can do the exact physics, time to correct general relativity, time to correct our approach to the Euler-Lagrange equation for trajectories, and it's time to basically realize that as we've been using Einstein's general relativistic equation, it's wrong. It's not only an approximation. Actually, it's wrong, especially in those areas where we make the measurements, which is when objects are in close proximity. That's when it fails the most. And even something as simple as the angular orbital momentum, we've gotten it wrong. Our close encounters are different, will be dynamically different than we've modeled them using the inverse square gravity law. So the basic issue is there something wrong with physics? Yeah. Can it be fixed? Yeah. And we've identified how it can be fixed, and those fixes are fairly straightforward. It's a matter of a will to do so. Whether anybody pays any attention to this or not, I don't know. But from here on out, I've got one more video in this general topic area. It'll be video 20, where I will editorialize a little bit more in terms of what's going on with general relativity. And then after that, I'm going to look into quantum mechanics. Now, with quantum mechanics, it's difficult to identify a specific instance in which the physics has been distorted or misused. That'll be a true exploration. What I will do is I'll use the same technique in digging into the antecedents to quantum mechanics. We know that anything that uses, at least I'm convinced, that anything that uses relativistic, like quantum electrodynamics, is wrong automatically because we've completely messed up everything we've known about special relativity. And the idea that the errors occurred 300 years ago have rippled down through 200 years to Einstein and an additional 100 years to the present time. It's time to really get our act together. And so from that perspective, I think I've made my case. There is something wrong, and it can be fixed, at least in part. Now, when you go on and look at quantum mechanics, it's not so clear. There's still puzzling things about quantum mechanics. Anything that contains the point mass, the hydrogen atom model, for instance, contains point sources, point forces, inverse square laws. So obviously quantum mechanics, at least at that particular level, since it uses the Euler-Lagrange equation to find solutions in spherical coordinates, we can improve it. Do we have enough knowledge to improve it? I don't know. That's one of the things I've got to identify. But as of this point, I believe, as I stated, I made the case. General relativity is fixable. But we have to go back, we have to fix all the other things along the way that led us down these dead-end paths that we've been on. And we now have a starting point for being able to move forward. We didn't have a starting point before. All these anomalies, errors, omissions, misuses haven't been recognized. And from a technology perspective, we haven't really needed to recognize it, but we do now. we've reached the point where there are many systems that are now affected by various aspects of the propagation of radiation and consequences of the electrodynamic portion of the 1905 paper by Einstein on special relativity. Not the least of which is the series of assumptions that were made and the inability to look back and to critically review things in light of what we've seen and what's happened in the ensuing years. So with that, I'm Luther Ney. Leave comments if you would, and pass the link for these videos on to your favorite physics teacher and see what their reaction might be.